Hello, my Sancha nerds. Welcome back to Fluid Mechanics. Today you're in for a treat in this video and the next, because we're gonna be deriving the continuity equation. You might have seen the continuity equation before. Should I give it away? A1 B1 equals A2 B2. We're gonna be deriving that using an intuitive definition of the chemical engineering main Bay equation, namely the mass balance. So the continuity is one form of the mass balance equation. And what is the mass balance? Well, currently I have about 35 videos on chemical process analysis, which is the fundamentals of mass balance in chemical engineering. And I'm still working on those videos while I'm still working on this. But if y'all need some review on mass balance, please check those out, because if you're stuck in the fundamentals, then we're gonna have a little bit of a harder time with the more advanced stuff. But we're gonna do a quick review of it today. So we can have a system, any system really. This could be a cup of water, this could be a giant tank, this could even be people in a city. Yeah, it's great. I love this equation because it's really quite intuitive in my opinion. So if we say some flow rate, let's say this is a tank of water, and we say that this is some flow rates coming in and this is some flow rate coming out. Well, a real quick definition, if we say that any variable, let's call it T dot with a dot on top, it's really going to be whatever that variable is divided by time. So for example, mass m dot is going to be mass over time. All right. So if we say that the flow rate coming in, m dot in, and m dot out, this is really the mass per time coming in, so kilograms per second of some feed, and kilograms per second of some feed coming out. And so the main Bay equation, when in doubt, accumulation equals in minus out. So if you're coming from my CPA videos, this is already drilled in your head. And please do check those out, because I got a ton of problems and more coming out. There's a lot of intuitive stuff there that really gets your noggin going. So accumulation equals in minus out. So what is accumulation? Accumulation is going to be the mass flow rate of this system with respect to time, right? Because if you imagine that there's some system, and if it's closed, it's going to be accumulating if the mass flow rate is greater than if the mass flow rate in is greater than the mass flow rate out. So accumulation is just whatever's growing, or it could be depleting over time if the mass flow rate out is greater than the mass flow rate going in. So dm dt is equal to, well, in this case we have the mass flow rate coming in minus the mass flow rate coming out. So this is your mass balance equation. And using this mass balance equation, we can use it to derive the continuity equation, like I said. So mass flow rate coming in. By the way, do you recall the definition for density? I'm sure you do, because density equals mass over volume, so therefore mass is density times volume. So using this definition, we can write the mass balance equation as such. dm dt is going to be the density times the volume of the system, okay? The change in the density times the volume of the system, which is equal to, well, actually, this is going to be a chain rule derivative, which we'll see later on. We're going to have to use a chain rule on this guy. We have to integrate our different equations. And the mass flow rate coming in is going to be rho volumetric flow rate coming in minus rho and volumetric flow rate coming out. Well, that's pretty good. Okay, well, what happens if, okay, we can work with this. We can make some assumptions. We can assume that it's going to be steady state. And steady state means that your time derivatives are going to be zero. So anything with the time derivatives is going to be zero. It's going to be negligible. Why? Because as I said in the other videos, I'm telling y'all, you got to check them out if you need some refresher on this. Because steady state means that it's in equilibrium, so there's no accumulation. So basically, this guy goes to zero. So we're going to say that zero is equal to, well, now we can factor out that rho. Well, let's leave it in for now, because check this out. And there's going to be v dot in minus rho v dot out. All right. What else do you know about v dot? Well, just for the sake of writing it, I can say that v dot is going to be v per time coming in minus v per time coming out. And so if we have this system where we have this into the board is going to be the cross-sectional area, and this is going to be your delta x, right? This is going to be your delta x. So the V in volume really is going to be what? Volume is going to be area times delta x. Now if we draw a nozzle with different areas, such as one where the nozzle is converging, you can say that this is going to be one area, cross-sectional area. This is going to be another cross-sectional area, A2. And this is going to have corresponding x values. This is going to be x1 and x2. Well, is that a little hint? We can replace this by saying that it's going to be 0 equals rho A x1 over t minus rho A, that's going to be A1 x1 and A2 x2 over t. Hey, does that look familiar? Well, from the dimensional analysis videos, this is why y'all need to check out my other videos and plug in my videos. So this is a capital V, but remember the lowercase v is going to be distance over time. So this guy, namely this guy and this guy, you can replace that as 0 equals rho A1 V1 equals rho A2 V2. Okay, so these are lowercase v's now, whereas before they were uppercase v's. And so if we move these to the other side, we're going to get that rho A1 V1 equals rho A2 V2. Okay, that's pretty interesting. And finally, if we assume constant density, we can cancel out these guys, and we're left with the continuity equation. Y'all can see that. I'll put it right over here. A1 V1 equals A2 V2. So these are lowercase v's for velocity. So this is the continuity equation. And what I want y'all to do is check out the units for this guy. So the units for density, or the dimensions really, do some dimensional analysis. Mass per length cubed, length squared, and length per time. What is that going to give you? Overall, it should give you dimensions of mass per time. Because this is still the mass balance. We're just working around the mass balance using areas and velocities. And what this is saying is that if you take the product of the area and the velocity of one section of a pipe, it should be equal to the area and velocity of another section of the pipe. And so if the area is greater 1 on one side, such as in this case, so this is bigger, then this product has to be equal to this, right? So we can say that A1 times V1 is going to be equal to some product. And if this is big, for this product to be equal to this value, mathematically this product has to be smaller. So in other words, if we know that the area of the first section is bigger than the area of the second section, such as in this case, then this velocity is going to be smaller than this velocity. Okay? Think about that mathematically, but now think about it physically. Have you ever taken a hose and the hose is running? You put your thumb over the hose and it's like starting to like really squirt out? That's because you're making a nozzle with your finger. So the area here is greater. And when you're making a nozzle, you're converging that area and forcing it through to the other side. Now, this is a little bit counterintuitive because, check this out. Y'all mind if I erase this? This is a misconception that I had. So say we're on a freeway, okay? And there's a lot of cars coming in over here. A lot of cars coming in over here. On the freeway, the velocity at this point at x1, this is the velocity here, and this is at this point at x2. On the freeway, the velocity here is less than the velocity here. Why? Because there's so many cars that are converging to the center right over here, and they're just like slowing down over here. So this is a lot of traffic, lots of traffic. So then I was like, wait a second, if this area is bigger than this area, and this velocity is bigger than this velocity, so then how does that make sense for the continuity equation? Because for mass balance, mass is conserved. Mass is how many molecules, right? Mass is the number of protons. You're adding up all the protons, mass is conserved. So what, despite the nature of physics, the first law of thermodynamics, this analogy does not apply. So this, do not think like a freeway for the continuity equation. Because, now let's redraw the nozzle again. So now we're drawing the nozzle one more time. So this is going to be area 1 and the velocity 1, and area 2 and the velocity 2. So here area 1 is greater than area 2 again, just like in the freeway. But here, at this point, we're going to count up all the molecules going through that area. And the way you do that is using the mass balance. Because we said what? We said that mass is essentially, when we derived it, rho A times the velocity. So you take the density of the fluid, take the cross-sectional area of that point you're looking at, and the velocity at that point you're looking at, that's going to be the total mass, the total molecules, and using molecular weight, you can even count, and Avogadro's number, you can count the number of molecules going through that section. And in fact, when we take mass transfer, we're going to be doing exactly that. So here, the mass flow rate is going to be here, right? So this is m dot 1, rho A1 V1. But what did we say about this? We said that m dot 1 is equal to m dot 2. So that is going to be m dot 2, rho A2 V2. So if we set these two equal to each other, m dot 1 equals m dot 2, these have to be equal to each other. In other words, all the molecules coming in here, let's say we count 14 to the power of 30 molecules coming in through here. There has to be 14 to the power of 30 molecules coming in here because mass is conserved. Conservation of energy. Conservation of energy. Right? Therefore, the rho A1 V1 equals rho A2 V2. And we said that, again, the A1 V1 over here is equal to the A2 V2. So that means this product has to be equal to this product. So that's why the analogy does not apply, because for cars, mass is not conserved. Because cars slow down as they converge. But for the flow rate, as this converges, it goes even faster. Which to me, that's pretty fascinating. As something gets closer and closer for fluids, and there are some exceptions once we get to the Mach number. When the fluids converge, it's a little counterintuitive because it's like, oh, I'm getting cramped. But that would motivate the molecules. It's a driving force. We're changing the pressure. Oh, we're starting to introduce, what did we talk about in the first lecture? Talking about momentum transfer. Momentum transfer. Now we're talking about changing the pressure in the system, and that's gonna, momentum, remember momentum is mass times velocity. Oh, very interesting. Keep that in mind. I'll see y'all in the next video. Click over here to get to my playlist. Don't forget to share this with your friends, family, and your dog.